Hello, this is a series of lecture on basic physical chemistry, a course in the Department of Chemistry, University of Lagos. So in this series of videos, we'll be talking about the basic concepts of thermodynamics. We'll also be looking at the first law of thermodynamics and its application to various processes. We'll also talk about thermochemistry. So let's start. Thermodynamics talks about energy changes, study of energy changes. Energy, as we all know, is the capacity, the potential to do any work, to carry out any work. It can be in various forms: electromagnetic, from various ways. It can be thermal, like in the cold ice cream, or in the hot soup. It can be mechanical, like a leaping frog. It can be nuclear, it can be chemical, it can be electro. Now, all these forms of energy can be transformed from one to another. And the process of how this is done is the focus of thermodynamics. So thermodynamics is the study of the transformation of these various forms of energy into another, and its effect on the properties of the system. So like every other thing, we have to look at the basic concepts in thermodynamics. The first is the universe. Everything that exists is said to be contained in the universe. But the universe can be divided into two, which is the system and the surroundings. The system, that's the part of the universe under investigation. It can be a test tube in the lab, it can be a classroom, and then the remaining part of the system of the universe is the surroundings, or the environment, or it's also called the reservoir. Now, the system is separated from the surroundings by a boundary. The boundary can be definite or it can be imaginary, but it's what separates the system from the surroundings. Depending on the nature of the boundary, we can have three different types of system. An open system, where we can exchange energy and matter. Most systems are around are like that. So when there's exchange of matter and energy, we call it an open system. For example, a hot cup of tea, as the steam is going out, that matter is being exchanged as the temperature is reducing, so that's heat energy being exchanged. Another example is the ocean. Another the type of a system is a closed system. In a closed system, matter is not allowed to go through the boundary from the system to the surroundings. Only energy is allowed. Like an ideal greenhouse, or another example would be a cooler, where you have a hot food inside, but it's covered such that steam is not allowed to go out. However, the temperature goes down. That's heat energy. And then the third type of system is an isolated system. In an isolated system, neither energy nor matter is allowed to be exchanged with the surrounding. An ideal isolated, closest to what we can have in an isolated system, is like a gas in a cylinder, a sealed gas in a cylinder, where the gas is not allowed to escape, and it's insulated, and there's no temperature exchange. So there's so isolated, it's insulated. So an open system, matter and energy. A closed system, matter is not allowed, but energy is allowed to pass through the boundary. So there are three types of a system. The state of a system still talking about the basic definitions in thermodynamics. The state of a system is described by variables, thermodynamic variables or state variables. So when we talk about the state of a system, we're talking about the condition in which the system is. So examples of variables, we can have the color, the luster, the hardness, the temperature, pressure. Those are most of the things that are variables. A set of logical attributes that can vary or change. Now the thing about these variables is that they can depend on the amount of the system, on the amount of substance in the system, or they may not depend. So because of that, variables are divided into two. So you can have extensive variables, also properties. These are such that depend on the amount of substance. An example is the number of moles. The more you increase the amount of substance, the more the number of moles increases. The mass depends on the amount, so it's an extensive property. Then the length is an extensive property. The other type of variables are the intensive variables or intensive properties. So I'm using this the two words property and variables interchangeably. So these are independent of the amount of of substance present. The boiling point is always definite the boiling point of water is 100 degrees Celsius, regardless of whether you have 100 grams or 10 grams of water. The density, so it's boiling point, density is another. So density, that's mass over volume. The ratio of two extensive properties is an intensive property. For example, the density is the ratio of mass over volume. Thermodynamics deals with systems in equilibrium. So when we say a system is in equilibrium, thermodynamics only deals with systems in equilibrium. So a system is in equilibrium when the variables of the system are constant. So when we say that the variables are constant, it means that even the system is not changing, or the system changes by an infinitesimal amount. So the variables are really constant. In the mechanical equilibrium, there's equality of force that balances each other. In the thermal equilibrium, there's no change in temperature. There's equal temperature throughout the system. And then in the chemical equilibrium, the chemical composition does not change with time. Even if a forward reaction is going on and a backward, the composition are still constant with time. So thermodynamics does not give information on how equilibrium was achieved or how fast it was achieved. It is only interested in the system that is in equilibrium. There's with respect to thermal equilibrium, the zeroth law of thermodynamics says that if you have a system A that's in contact with system B and they are both in thermal equilibrium, if B is in contact with another system C and they are in thermal equilibrium, invariably A is in thermal equilibrium with C. As earlier mentioned, the thermodynamics studies energy changes, and that the state of the system is described by variables. Some of these variables depend only on the initial and final state of the system. They depend only on the state of the system. Such variables or functions are said to be state functions. They depend on the state of the system, and once there is a process that changes the state of the system, the change in value of that variable is just the final value minus that of the initial state, or given this definite integral. It does not depend on how the change of states was. Examples are temperature, pressure, internal energy. We'll define this in a moment. The other functions that depend on how the state was achieved and not on the current state of the system, these are called path functions. They're also called process functions. Examples, the main examples are eat and work. The equation, the path variable, does not apply, that the final state minus the initial state, because path functions do not depend on the state of the system. They depend on how the system was achieved. So they are represented by this indefinite integral. Thermodynamics is applied to matter. Matter is anything that has a space, that has mass and occupies space. It exists in three different forms: gas, liquid, and temperature. And some of their characteristics, the gas assumes the shape of its container, the liquid same thing, but it doesn't have the volume of the container. However, all the states, the solid, gas, liquid, they have an equation that's used to model their behavior. For example, for an ideal gas, the equation used to model an ideal gas is PV equals nRT. An equation of state relates the variables that describe the particular state of matter. So this is an equation of state for an ideal gas, and for a real gas, this is an equation for a real gas, where P is the pressure, and we know pressure is a measure of the force occurring due to collision with molecules, between molecules and surface, and its SI unit is a Pascal, which is Newton per meter squared. V is the volume, that's the space occupied by the gas. N is a number of moles that's related to the amount in grams. R is a gas constant. R is universal gas constant. And T is a temperature. Then capital N is the number of molecules. It is related to the number of moles and Avogadro's number. K is Boltzmann constant. There's a relationship between R and K. R is the Boltzmann's constant multiplied by the Avogadro's number. That's the number of particles in 1 mole. And A and B, so we have pressure, number of moles, volume, but then we have two additional constants, A and B, which are called van der Waals constants and vary from gas to gas. So in the next video, we will talk about internal energy, work, and equipartition theorem.